Let's look at this problem from a recent web assign. In the problem, we have a family traveling through the park, driving down the road at 10 meters per second when a deer jumps in the road 62 meters ahead of the vehicle. The driver applies the brakes to produce an acceleration of negative 2.6 meters per second squared. The problem asks, what is the maximum time allowed for the driver to react before applying the brakes if the vehicle is to avoid hitting the deer? There's a couple things to unpack in this problem. One, you have to think about how reaction time works in a vehicle. When you see the deer, you don't immediately press the brakes. There's a period of time where you have to process what's going on. And during that processing or that reaction time, the car continues to move. And because nothing else is stated, we can assume that car is moving at the same speed it was going at prior to applying the brakes. So when you start seeing problems like this, where you have two types of motion, in this case, constant velocity, a car cruising at the same speed, and a braking period where you're accelerating or slowing down in this case, you have to look at this problem as two different types of problems that are related because they're on the same number line or road in this case. So I'm going to draw a picture and start to identify those different parts of the problem. So let's start. We've got a car driving down the road. I'll draw an arrow to represent the velocity it's moving at, 10 meters per second. And here's our road. Now this car, we'll call this initial position 0 meters. What we know about the problem is up ahead is our deer. So I'll draw a little crude deer with some antlers. And that deer is located at a position 62 meters away. That's what I know in the problem. Now, why that is important is because we're trying to find the maximum time. Anytime they ask for a max or minimum time, we're looking for that extreme case in which the driver, in this case, would not have reacted in enough time. If the driver hits the deer, the driver has taken too long to react. And if he stops short of the deer, he hasn't utilized all of his time. So in order to find the maximum time, we're going to place the car right at the deer when it comes to a stop. So we're going to call that the final position. And if we start at 0, that final position would have to be 62 meters. Now, right now I have initial and final, but that's assuming those cars are accelerating at the same rate. But as we know, this car actually cruises for quite a bit before applying the brakes. So really we have this middle scenario where the car is at a position and still moving at 10 meters per second. And so we really have a two-part problem. I'm going to label part 1 from those two positions, and here's part 2 where the car is decelerating. Part 1 is a constant velocity. The acceleration in part 1 is 0 meters per second squared because the car has not changed its velocity. We could assume it's been in cruise control while he's reacting. Whereas part 2, we have an acceleration that pushes left against the car. That's what causes it to slow down, which is why it's a negative 2.6 meters per second squared. Part 1, there's a time associated with it, which we don't know. And in fact, that would be our reaction time. That's what we're looking for. Part 2 also has a time that's unknown. That would be the time it takes for the car to come to rest once the brakes are applied. We know that hopefully this car will have stopped at this point, and so it's going at 0 meters per second right here. And we can start to throw some labels on these positions. So this initial position would actually be the initial position for part 1. And when the brakes are applied, it'll be at the final position for part 1, which coincidentally is also the initial position for part 2. And that's going to be important to solve the problem. And this 62 meter position is the final position for part 2. And we have an initial velocity for part 2 is 10 meters per second, which is also the final velocity for part 1. They're connected to the same velocity, whereas this is the initial velocity for part 1, 10 meters per second to the right. I think I have everything worked out at this point. We have a couple things we don't know. Now, in my drawing, I've kind of outlined all the variables, but what I found is a good strategy is to put them in a table. We have 3 equations that we can use. We have equation 1, which is our position equation. 1/2 plus v initial t plus x initial. We have our second equation, which is v final equals at plus v initial. And we have a third equation that we introduced, which is really just an algebraic manipulation of the two, which says that v final squared equals v initial squared plus 2 times a times delta x, which is x final minus x initial. So with these three, what we call them kinematic equations, we can solve for any missing piece as long as we're given enough information. So I'm going to set up my two tables. Table 1, we have A1, T1, V initial 1, V final 1, X initial of 1, and X final of 1. A is 0 meters per second squared. We don't know the time. This is actually our reaction time, the time it takes for him to react and press the brakes. That's the value we want to answer the question. He starts moving at 10 meters per second, and he finishes at 10 meters per second. He starts at 0 meters, and going at that velocity for that period of time, he should finish at some position, which we don't know. Now, if you look at those three equations, because the initial and final position is 0, the acceleration is 0, we really don't use the first equation. The only equation we have is equation 1, which says that x final equals 1/2 of 0, so that goes away. So that's just vt plus x initial. That's the only equation that we can use when we have constant velocity. Now again, this is using all three, but if the velocities, if we don't have an initial and final, if it's just v and a is 0, all that simplifies. The second two equations are kind of meaningless. So now let's look at the second table, and this is where we're going to start to work. A2 is negative 2.6 meters per second squared. T2 is a time we don't know. The initial 2 is 10 meters per second, right? It's the same velocity that we started with. And the final 2, we know that this car would have to stop, so we're going to put 0 meters per second. Our initial position of 2 we don't know, but our final position at 2 would be at the deer, 62 meters. And what's going to connect the dots here is that the initial position of 2 and the final position of 1 are the same. And so if we can find that, then we can find T1, because that would allow us to have only one missing piece in part 1. So we need to find the initial position in part 2. And if you look in your equations, all right, here are the things we have for part 2. We have A, so I'll put a little dot over all the things that we have. We have the final position, and we don't have the initial, we have the initial velocity. But look at that first equation, we're missing time and an initial position, so we can't use that one yet. Now here we have V final, we have V initial, we have A, and we're just missing time. So we can use the second equation to find time, and then plug time into the first equation. However, we also have this third equation, which we have the final velocity, we have the initial, we have A, we have the final position, and the only thing we're missing is x initial, which means since we're missing time, we can use this third equation. And in one equation, we can actually find the variable we need to bridge the gap. So I'm going to take that VF squared equation, and in one step, I'm going to plug in what I have. I have 0 squared equals, the initial is 10, we need to square that, plus 2 times negative 2.6 times 62 minus x initial. And now it's an algebra problem. So I got to be careful with my distributing. This gives me 0 equals 100 plus negative 5.2 times 62 minus x initial. And again, we're going to distribute the negative 5 there and there, which gives us 100, pull out my calculator, 5.2 times 62 is 322.4. So negative 5.2 times 62 is negative 322.4. And negative 5.2 times negative x initial is plus 5.2 x initial. Again, that's technically for part 2. And I'm going to start to combine our terms here. I believe that should be negative 222.4 plus 5.2, x initial 2. We'll add it to the other side and divide by 5.2. 222.4 equals 5.2, x initial 2. So x initial 2 is equal to, subtract 100 and divide by 5.2, 42.77 meters. So I can write that in here, 42.77 meters. So that is the position on this track, 42.77 meters, which means we went another 20 meters to stop, which now means that this car has 42.77 meters of distance in order to react. And so the last step would be to plug that in here. 42.77 meters equals the velocity, 10 meters per second, times our reaction time, plus 0. And when we divide by 10, we get time to be 4.277, call it 4.28 seconds. So that would be the time it would take for him to react. And in that time of reacting, his car would travel 42 meters. He would then apply the brakes over the next period of time, which we actually didn't solve for the time. We could if we wanted to plug it in. Just to show you what that time would be, if I take that here, 0 equals negative 2.6 t plus 10. And so time would be 10 divided by 2.6. The time that he actually stops would be 3.85 seconds for time 2. So that's the time it takes for him to actually come to a rest at a position of 62 meters. So as you see, a lot of work. It's important to organize your work and draw a picture and understand how the two pieces connect. You'll see a lot of problems like this where you have two parts, either two different accelerations, or you'll have a period where there's an acceleration, a period where there's constant velocity. But they're usually related because they're on the same either time frame or the same number line, if you want to think of it that way, as a one-dimensional problem. Best of luck.